Welcome back. Today we're looking at large multimodal reasoning models, LMMs. I mean, the progress lately has been just incredible, hasn't it? Tackling really complex stuff, math, science, things that feel like deep research problems.
Absolutely. And a lot of that push, especially recently, comes from using reinforcement learning, RL, to fine-tune these models after their initial training.
Right, RL helps guide them. But anyone working in this area knows there are a couple of big hurdles. First, just finding enough good, open, long chain of thought data.
Hmm.
The step-by-step reasoning is tough.
That's always a challenge, the data.
But the second one, and this is really the technical knot we're untangling today, is how unstable RL training can be. Specifically, this issue called gradient vanishing.
Yeah, that instability is the real bottleneck. It's like the learning signal just fades away. So our goal in this deep dive is to explore a proposed fix from the MMR1 paper, Variance-Aware Sampling, or VAS.
Okay, VAS. So how does it actually stabilize things?
Well, to get VAS, you first need to understand the tool it's trying to fix. That's Group Relative Policy Optimization, or GRPO.
GRPO. I've heard that mentioned a lot. It's pretty standard.
Very standard. It's popular because it's, well, efficient. It scales well for language models, multimodal models. It's the workhorse.
But it has this hidden problem.
Exactly, this inherent flaw. GRPO is just really susceptible to gradient vanishing. It calculates the gradient based on relative advantages comparing how good one answer is versus the average of others for the same prompt.
Okay.
So if all the sampled answers get roughly the same reward, maybe they're all wrong or maybe they're all right. The reward variance is low.
So the differences are tiny.
Right. And when that happens, the relative advantage calculation just collapses towards zero.
So let me see if I get this for you listening. Imagine the model is trying a hard math problem. If it gets it wrong 10 different ways, or maybe gets it right every time but in the same basic way, the rewards all look similar, low variance. So the model doesn't get a clear signal on how to actually improve.
Precisely. The optimization signal becomes incredibly weak, almost useless. And that leads to the unstable, sometimes stalled training we see. It's a fundamental problem for RL unimodal or multimodal.
Which is where VAS comes in. It's designed to tackle that head on. It's not just taking random data,
Yeah.
it's selecting it strategically.
Exactly. It's a dynamic data selection strategy. Instead of passively accepting low variance data that kills the gradient, VAS actively seeks out data that will prevent the vanishing problem.
And there's solid theory behind this, not just intuition.
Oh, absolutely. This is the really compelling part. They proved mathematically that the reward variance provides a lower bound on the expected magnitude of the policy gradient.
A lower bound. So
Yeah.
more variance
A
guaranteed.
stronger minimum signal, yes.
Yeah.
They showed that the expected progress the model makes in a single update step is linearly tied to the reward variance of the prompt it's learning from.
Okay, that's powerful. Increase the variance, you guarantee you're strengthening the learning signal and stabilizing training.
It's a principled approach, not just tweaking parameters, but addressing the root mathematical cause.
So if high variance is the key, how do you actually find those high variance prompts efficiently? You can't check them all manually.
Right, you need an automated way. That's what the Variance Promotion Score, or VPS, does. It's the practical tool VAS uses. It scores prompts based on their potential to create that needed reward variance.
And this VPS, it's not just one number, is it? And I think you mentioned it combines two ideas.
Correct. It has two components working together. The first is the Outcome Variance Score, or OVS.
OVS, outcome variance.
Yeah.
So how likely is the model to get the answer right or wrong?
Basically, yes. Think of it like finding prompts that are just right in difficulty. OVS is calculated as PX times 1PX, where PX is the pass rate for that prompt.
So it peaks when PX is 0.5, like 50% pass rate.
Precisely. If the model gets it right 100% of the time or wrong 100% of the time, the outcome is predictable, variance is low, OVS is 0. It favors those prompts right on the edge of the model's current ability, where it gets it right about half the time. That's where the uncertainty, and thus the variance, is highest.
Okay, that makes sense for maximizing reward signal based on correctness. But what if the model gets it right 50% of the time, but it's always making the same kind of reasoning mistake on the failures, or using the same path on the successes? Don't you want variety in the how as well?
An excellent point, and that's exactly what the second component addresses. The Trajectory Diversity Score, or TDS.
Trajectory diversity. So this looks at the actual reasoning steps, the chain of thought.
Yes. While OVS looks at the final outcome, TDS looks at the diversity within the generated responses themselves. It uses a diversity function, something like inverse self BLEU or distinct NAT over the different reasoning paths, trajectories, the model generates for a single prompt.
So it encourages the model to try different ways of thinking.
Exactly. It pushes the model to explore different solution strategies. This helps keep the gradient signal rich and informative, especially for complex problems where just looking at the final answer might not tell you enough, or the feedback might be a bit noisy. You want diverse exploration.
Okay, so you have OVS for outcome uncertainty and TDS for reasoning path diversity combined into the VPS. How does VAS actually use these scores in training? Do they just train only on high VPS prompts?
No, that could be risky too. They use a clever mix. They have a hyperparameter, lambda, that controls the ratio.
A mixed ratio, okay.
So each training batch is built in two parts. One part, proportional to lambda, is sampled based on the VPS scores, prioritizing those high variance informative prompts.
Giving them extra weight.
Right. But the other part of the BEP is sampled uniformly at random from the whole data set. This ensures the model still sees a broad range of data and doesn't sort of overfit to only the hardest stuff and forget its general knowledge.
That sounds like a good balance. And the model's abilities change as it trains, so these VPS scores must need updating.
They do. The scores are recalculated periodically, say, every update training steps to reflect the model's current learning frontier. What was hard before might be easy now, and vice versa.
This whole VAS system sounds robust, but you mentioned it was paired with specific data curation too.
Absolutely critical. The VAS technique worked hand in hand with really careful data preparation across two stages. First, for the initial supervised fine-tuning, the cold start phase.
What did that data look like?
It was large, about 1.6 million long chain-of-thought examples covering math, general knowledge, charts, document stables, and science. But here's the key. They filtered it aggressively. They only kept medium and hard examples based on initial pass rates.
So forcing it to learn from challenging examples right away.
And then for the second stage, the RL training, where VAS was actually used.
They focused the data even more.
Yes. Around 15,000 RL question-answer pairs, but heavily weighted towards hard math and logical reasoning problems. The explicit goal was to push the model towards strong general reasoning, using VAS to make that difficult learning process stable and effective.
And did it pay off? What were the results?
The results were quite strong. The MMR1 7B model they trained achieved an average score of 58.4 across several tough math and logic benchmarks. That set a new state-of-the-art for similar-sized reasoning MLLMs at the time.
State-of-the-art on things like MathVerse, MathVision.
Right. Logic Vista, ChartQA2, really solid performance across the board.
But beyond the benchmark scores, did they see evidence that VAS was mechanically doing what the theory predicted during training?
Yes, and this is where the theory really connects with practice. Models trained using VAS showed consistently higher actor gradient norms compared to just using the standard shuffled data.
Higher gradient norms,
Yeah.
meaning the learning steps were stronger, more confident.
Exactly. Bigger, more meaningful updates instead of tiny, noisy ones. It directly supports the idea that boosting reward variance produces stronger, more reliable gradients.
Any other indicators?
They also saw higher and much more stable policy gradient clip fractions. A high, stable clip fraction suggests the model is effectively using the strong signals generated by VAS without going haywire or making overly drastic, unstable updates. It points to more efficient use of each training sample.
More stable, more efficient learning. And you can even see this in the model's outputs, right? I remember seeing an example.
Yeah, figure 4 in the paper had that complex geometry problem. Finding an angle required multiple deduction steps.
And the model's reasoning wasn't just a lucky guess.
Not at all. The generated chain of thought showed really systematic problem solving. It broke down the problem, planned steps, executed them, even included checks and considered alternative ways to get the answer. That kind of robust, structured reasoning is likely a direct result of the stable optimization VAS provides.
So bringing it all together, the MMR1 success seems to be this synergy between very carefully chosen, difficult data and this theoretically sound stability mechanism, VAS.
That's the key takeaway. It's the combination that delivers such effective RL for these advanced multimodal reasoning tasks.
Now, the researchers do mention that calculating these VPS scores adds some computational costs. They suggest ways to manage it, like updating less frequently or only on subsets of data.
Right, there's always a trade-off.
Which leaves us with a really interesting thought for you to consider. We have VAS, which offers this mathematical guarantee of stability and progress during training. How do we best balance leveraging that guarantee with the ongoing need for maximum computational efficiency, especially as these models get even larger and more complex? That seems like a crucial question for future work.